Solving a logarithmic equation challenges our ability to rewrite the logarithmic equation as an exponential equation. This requires that we demonstrate a pretty fundamental understanding of logarithms, that is, that it is just a rewrite of an exponential. So remember the entire point of a logarithm. The entire point of a logarithm is that this is the base. This is what we previously would have known as the exponent, and that is what we previously would have understood as the output, not the input. The purpose of a logarithmic expression is that it inverts an exponential expression. So if we're going to rewrite this as an equation, let's just reverse that inversion and go back to an understanding of logarithms that we already know. Namely, that 4 squared would have to equal x plus 3. We know that 4 squared is 16. And finishing the solving, we get x is equal to 13. For these type of equations in particular, it's never a bad idea to check your answer. Let's take our 13, put it back into the logarithm, and say log base 4 of 13 plus 3, log base 4 of 16. Well, what's the power of 4 that gives you 16? That would be a 2, and that checks out. So working through the steps of rewriting the logarithm as an exponential allows us to get this output, or this input, back to being the output. Similar situation here with a slightly more complicated base and a slightly more complicated input of the logarithm, output of the exponential. So here's our base, and here's our exponent. So we'll say 2x, all of that to the power of 2, is equal to that expression that we previously were attempting to take the logarithm of, x squared plus 9x minus 6. The product 2x to the power of 2 is really just 4x squared is equal to x squared plus 9x minus 6. Moving the terms so that everything is on the same side, I'm going to push everybody that way. And we're going to end up with 3x squared minus 9x plus 6 is equal to 0. Notice that each of these terms is divisible by 3, and the entire expression is equal to 0. So we're just going to divide everybody by 3 in an effort to clean up all of those coefficients. And then we just factor and solve the resulting binomial equations, giving us two answers, x is equal to 2 and x is equal to 1. Similar to what we did in the last question, it's worth taking the time to check those two answers and see if they actually are solutions, especially because we went through a lot of different algebraic steps to get there. The likelihood that we make a mistake increases based on the number of steps that we have to take. So we want to make sure we really got to the end, especially because we have x showing up in two different places. We've got an x here and an x here, but then also the x that's over there. So we're going to get rid of all of this work that we just did, and let's leave the two answers, 2 and 1, and we'll test both of those to make sure that they are actually solutions, going through the work of back substituting. So let's first back substitute the 2. So we have log base 2 times 2 of 2 squared plus 9 times 2 minus 6. That's log base 4 of 4 plus 18 minus 6. That's log base 4 of 16, which is exactly what we saw in the last example too, and that checks out. So now let's check our other solution of 1. Log base 2 times 1. 1 squared plus 9 times 1 minus 6. That's log base 2 of 1 plus 9 minus 6. Log base 2 of 4. And that, of course, is also 2. And that checks out. So despite having to go through all of that long algebra, despite having to use what we understand as Algebra II skills, solving quadratic equations by setting them equal to 0, we go through all of those steps, realizing at the end, we want to make sure and verify that our solutions are correct. The reason that we want to verify our solutions as being correct is that there's a possibility they won't be. And that's what you'll see in the next video.